How can the data obtained from CV and LSV tests be used to improve the design and selection of electrolytes for batteries, especially in terms of maximizing the ESW and ensuring long-term stability? How do these tests help differentiate between various electrolytes with respect to their electrochemical stability, and how can they be used to guide the development of new electrolyte materials with improved performance? What other important electrochemical characteristics can CV and LSV tests reveal about an electrolyte's behavior during cycling, and how do these findings affect its overall suitability for use in energy storage devices? Can Davis Zurns manufacture solid-state sodium-ion batteries made from seawater in Latvia? Why is understanding the formation of SEI and side reactions critical to the development of safer and more efficient batteries, and how can this knowledge be used to mitigate potential issues with electrolyte degradation? How does EIS, electrochemical impedance spectroscopy, complement CV testing in studying the electrochemical properties of electrolytes, and what makes it an effective method for this purpose? What key components are typically found in an EIS curve, and how do these components provide insights into the electrolyte's electrochemical behavior? How does the high-frequency semicircular part of the EIS curve correspond to charge transfer impedance, and what does this reveal about the electrochemical processes occurring at the electrode-electrolyte interface? What does the low-frequency sloping line in EIS curve represent, and how does it relate to the diffusive properties of the electrolyte? How can the EIS curve be used to distinguish between different types of impedance that arise during electrochemical processes, and what information can be extracted from both the high and low-frequency regions? What specific electrochemical properties can be assessed using EIS that might not be as clearly understood through CV testing alone? And why is this complementary approach important in characterizing electrolyte performance? How can the impedance data obtained from the high-frequency and low-frequency regions of the EIS curve help in evaluating the efficiency and kinetics of ion transfer and charge storage? What role does EIS play in understanding the resistance and capacitance of the electrolyte? And how can it be used to optimize electrolyte formulations for better performance in energy storage devices? How can EIS be applied to investigate and characterize the behavior of specific components of the electrolyte, such as ionic conductivity, interfacial resistance, or double-layer capacitance? And what does each of these components tell us about the electrolyte's overall performance in real-world applications? Can you help Davis out? What employees is needed to build it?